Hi everyone. Thanks for hanging around. And thanks again to Dr. Lee to speaking to us about quantum computing and robotics. And we're gonna build off of what we talked about this morning. We started with QAOA, and that was our first glimpse at a variational circuit. That's a circuit where we have parameters that we are learning using classical optimization methods to update as we proceed along and to learn that way where we're doing classical optimization but calculating some of the difficult portions on quantum computing. So this is going to be another code walkthrough. I have the notebook saved in the chat, and I stole this. Well, I took a notebook and heavily modified it from the utility quantum computing set. There's an entire course on designing variational quantum circuits on IBM Quantum, and this is kind of stolen bits and pieces from that. So variational algorithms. You'll see this term a lot, but all a variational algorithm is that instead of being a purely deterministic, hey, rotate this, this gate by pi radians in the x direction. Instead of saying pi radians, we're going to make that a parameter, theta, that we can adjust and update with classical optimization. All right? So these parameterized circuits are constructed by hand to find that variational form. You're going to have layers of parameterized gates that are repeated multiple times. This is another aspect of this where we'll typically have an encoding layer that is encoding our data into the circuit. In our machine learning, that's our x, our feature vector. So we'll encode our feature vector into our circuit, and then we'll have an ansaetze. That's that part of the circuit that has those learnable parameters that are being updated and learned. And then we'll repeat those multiple times to increase the expressivity of this circuit. Trade-offs exist between speed and accuracy while exploring the search space, kind of similar to traditional machine learning. Typically, you can get a richer state space through quantum circuits that have more repetitions or that include more features, but we have to sacrifice speed with that. Additionally, we have the noise concerns whenever we're dealing with quantum computing, and that while a deeper circuit on paper would give us a better result, we have to fight the accumulation of noise that occurs when we do that. So there's that trade-off. So they have this little diagram. Okay, so you're going to start with the default state. Your quantum circuit normally starts with all the qubits in the 0 state. Okay, and then you're going to use your classical reference state to encode your quantum reference state. Okay, you may have application-specific ways that you encode those reference states. Then you're going to prepare your ansaetze. You're going to design a parameterized quantum circuit. All right, you have heuristic ansaetze. You also have problem-specific. It all is kind of dependent on what you're trying to do. But you're always going to start with initializing your problem, preparing your ansaetze. Then you're going to evaluate some form of cost function. This morning we talked about with the QAOA is that we were minimizing that cost function, which was just the inverse of our the number of edges that we cross while splitting the thing into two components. And then we're going to try to optimize our parameters to get results. We're going to use classical optimizers from something like SciPy. It could be from a more deep neural network. It could be through local or global optimizers. And also sometimes we'll have what's called warm starts, where we'll start training in classical, let classical get us part of the way there, then hand it off to quantum to try to solve those final steps. So parameterized quantum circuits, we have a set of variational algorithms that we encode these states, that psi of theta, where we start with a 0 input state and we parameterize the encoding of the features. So in this code here, we import quantum circuit, which is how we normally do our quantum circuit, and I'm showing another class that we import here is parameter. We set theta as a parameter theta, and then we're going to encode our information on qubit 0 by theta. So we're, instead of rotating by pi radians, which is what a normal X gate would, we're going to rotate by theta radians. And in this picture down here, you can see that instead of rotating by pi radians, we're just representing that we're going to represent it, or rotate this by theta radians. And so that allows us to have a placeholder there that we can optimize later on. Now, we're going to initialize a set of parameters here. This is just arbitrary initialization, but I make an angle list, which is pi over 3, pi over 2, and I'm taking my quantum circuit that I've designed here, and I'm assigning these parameters to those circuits. So whenever I draw my circuit, I see that here I applied pi over 3 radians, here I applied pi over 2 radians. I can apply different angles to these via those parameters. We're leaving ourselves a knob that we can tune to where we can affect what the output of our circuit is. So we take our reference state where we encode our information in, and we want to get to our target state. For that, we have to pass it through the variational form, which is our ansatze. So, our final quantum circuit altogether is that we take what information we've encoded into our circuit through our feature vector x, multiply that by our ansatze to get the final state. Now, an aspect here is that quantum circuits' greatest strength is also its greatest weakness. So any quantum circuit on n qubits represents 2 to the n possible states. So any n qubit system is going to be high dimensional. So if you have a feature vector that's 10 elements long, that means your feature space is 1024. Now that's not insane for a modern neural network to optimize 1,000 elements, but we're starting to get to this very, very high dimensional space that's difficult for our neural networks to solve. Whenever we get up to something like, let's say 30 qubits, now we're talking about a billion parameters, or not a billion parameters, but we're representing a billion dimensional space. So oftentimes we're going to impose constraints on the variational form to only explore the most relevant states. We are going to truncate our ansatze, and we're going to take a look here about some of the common designs that we get into. So if you don't have problem-specific information for you to kind of warm start your ansatze, whether you're hard coding that or whether you're learning that on a classical optimizer, a lot of times what we're going to do is just try to minimize the number of parameters that we're using. We have to remember that with a smaller search space that we can optimize this faster, but also that by reducing that search space, we may be excluding our accuracy, while at the same time acknowledging that deeper circuits have more noise. So, it's the basic thing here is that more parameters means higher probability of a precise solution, but means longer execution time, higher circuit depth, and more noise. So an n-local circuit, this is one of these kinds of ansatz that we define, where n could be 2, could be 3 or higher. It's very efficient because it uses very simple and local gates, and it just captures correlations between neighboring gates or neighboring qubits. So you're going to alternate rotation layers and entanglement layers. So each rotation layer is going to act on an n number of qubits, and it's going to be like a x rotation or a z rotation. And then you're going to use an entanglement layer, where if it's like 2 local, it would just be cx, where we're just entangling 2 adjacent qubits. Or we could have like 3 local, which uses a Toffoli gate, which isn't something that we've covered a lot yet, but you can provide entanglement between more than 2 qubits. So a 5 qubit n-local circuit we're going to define here. So I set up my parameter, theta here, and I have n-local that I'm applying this on 5 qubits. I'm going to use an Rx gate and a CRZ gate for my rotation blocks. I'm going to use this Toffoli gate, or this controlled X gate, I'm specifying how I want entanglement to be applied here, and I specify here that I want the repetitions here to be 2. And so this builds me a circuit that looks like this. So all of these thetas here are our tunable parameters, where we can update how much we're adjusting these angles by some constant scalar multiple to learn what the best way is of extracting the information we want out of this. Now, if you just wanted to use controlled X's instead of these Toffoli gates, you would have a 2-local circuit, where you're just providing this entanglement between, one qubit and another qubit. So similar to before, you can use n-local or 2-local, and here I'm just using rotation blocks of Rx and Rz, and then I just have this linear chain. So this is relatively efficient for modern hardware. I'm not fully connecting everything. You'll notice that qubit 0 is not connected to qubit 4 directly, but this allows us to keep the circuit shallow and to efficiently represent everything. Another efficient circuit type that we'll see is SU2, and the SU2 is a type of gate. Okay, it's a class of gate. So, I can designate my SU2 to have 4 qubits. I'm going to use Rx and Y gates and provide linear entanglement, and I'll end up with a circuit that looks like this, where I still have these theta parameters that I'm learning and updating, but still a relatively shallow circuit for having 4 qubits. You can become more problem specific, where you can restrict the circuit search space. Perhaps instead of searching full superposition, you exclude some possibilities that aren't possible in your search space. I'm not diving into this too much more here. IBM has a really great tutorial talking about ways of constricting that search space. So this is how we build ansats. All right, we're going to initialize our problem, where we're going to encode our reference state, where we're starting from. We'll prepare our ansats. After that, we'll evaluate the cost function. So we'll, measure our cost, what our output of our circuit is, but then we need to optimize these parameters. So this is the handing back and forth between the quantum and classical. All right, we prepare, this is our pre-processing step. All right, once the ansats is prepared, we run the ansats and get our cost, what our loss is for this function. Okay, then we're going to pass it back to classical to optimize, to update these parameters and run it again. So this is another example of the max cut problem, that QAOA problem from this morning. All right, I have a basic graph that I've laid out here, and I'm trying to most effectively cross each edge once while dividing these nodes into 2 distinct groups. All right, so we're still going to have our Z operators, where we're getting that expectation value through the Pauli's, and we'll build our circuit just like this morning. We can deconstruct it and show how this is all connected. But what we'll do then is we'll begin optimizing this. This morning we used the Kobila optimizer. And so we'll use that optimizer to start adjusting, to turn these knobs and all these little theta values to find how best to represent our problem. This is feeding into quantum machine learning. So this QAOA example is fairly constrained on how everything's connected, but we can encode our feature vectors directly into our quantum circuit and then train on these parameters that we're adjusting here and learning, just like we do with the weights in a deep neural network, where we can allow our optimizer to adjust these using something like a ZZ feature map which is a method of encoding this data to learn what the best result is. So with this, this is a very basic example, only 2 qubits. I have an X vector that's only 2 elements long. I use the ZZ feature map to encode my data. I make a 2 local ansats, and I put those together with this compose function, and I end up with this. I can then use SciPy's minimize function and specify the optimizer that I want to use, or any other type of optimization framework that you're familiar with from neural networks, and learn these parameters to make the predictions that I want. So it's how to prepare these parameterized quantum circuits is you're going to encode your data, you're going to have your ansats with the tunable parameters, and then you're going to classically optimize them. So you'll prepare you start in the 0 state, you encode your data with this reference preparation, and then you pass it through the ansats. Do you have any questions on that? All right, guys. Thanks for sticking around for this, and thanks for attending today. Tomorrow, we're going to be talking about noise and error visualization, as well as, let's see, in the schedule, we'll have noise and error visualization, like applying zero noise extrapolation or dynamical decoupling. We'll be talking about avoiding barren plateaus when updating these variational quantum circuits, how we avoid that. And then Thursday is for code examples and walkthroughs mostly. So please start dropping comments on if there's a specific algorithm that you would like a deep dive on or something like that, and I'll see if I can accommodate that. Also, we're done with guest lecturers largely, but we're going to be talking tomorrow about internships, summer schools, and jobs, some of the opportunities that are available there for that, as well as how to prepare for that. And then on Thursday for our final lecture session, we're going to talk about what to do now. How you can stay involved with quantum computing through the quantum computing group here. Talk more about what that looks like with your college career, whether you're an undergraduate, a master's student, or a PhD student, and try to prepare us for moving forward. All right, guys. Everyone, please have a great day, and I look forward to seeing you tomorrow.